Hello and welcome. This is actually a very simple problem disguised in a complex looking statement. So we don't need to really know much about turbine to solve this problem. You'll notice that in this problem, steam enters a turbine uh, with these given properties: 1000 kPa, 500 degrees Celsius, even the mass flow rate is given. And if the velocity is not to exceed this amount, what is the minimum area of the inlet? So the entire question is about the inlet state 1. We don't have to care about what happens in the turbine, what is the shaft work, what is happening in exit. So all we have to do is to figure out what's going on here. We know that m dot equals rho AV, and essentially the answer lies there that if the velocity increases, given that m dot doesn't change, density doesn't change because 1000 and 500 degrees Celsius, the state is fixed. So density, which is inverse of 1 over specific volume, inverse of specific volume, will not change. So if velocity increases, area decreases. And given that area is 30 meters per second, all we have to do is to find this. So obviously, it's a flow state problem. We'll use a PC because it's a phase change. Steam is a phase change fluid, so we will use a PC FlowState-TESTapp. I have already logged in as a student here, so we go to the TESTapps tab and go to the state, flow state, and pick up PC model and go to the leftmost tab to launch the app. So in the I/O panel, we gather the given information, which are, so as we click, it goes into the input mode. We can write down a comment line, given values. P1 is given in kPa, 1000 kPa. Similarly, I have already compiled all the given information in this page. So P1 is given, T1 is given 500 degrees Celsius, velocity 30 meters per second, and m dot 1 is given. So now it's time to go to the state panel and populate the given variable. T1 is T1 degrees Celsius. And you can always do a calculate to make sure, oh, I made a mistake here. Let's go back to the I/O panel. The mistake is that I haven't, after entering this variable, I haven't press the calculate button. Only then the variables are registered. And now if we come back here, you will notice if I do a calculate, it will pick up that value. So P1 is given, then T1, vel1, and m dot 1. Let's enter that. T1, P1 kPa. The velocity is given to us, so equals vel1 kPa. The leading zero is wiped out when you click calculate, so it doesn't matter. Oops, velocity is of course not in kPa, in meter per second. The white background reminds us that we made a mistake. And m dot 1 is also given, equal m dot 1 kg per second, and the unit here is kg per second. So everything kind of works out. So really the area has been already calculated for us, but the answer they want is in centimeters square. So we can say minimum area in meter square equals A1. So minimum area, let's just call it A because A is a standard variable. So instead of area, we'll just call it minimum A, or even better, it's always a good idea to start the variable name with a standard symbol. Area minimum in meter square is A1. Area min in centimeter square would be area mean meter square times 100. Oops, 100 times 100. 1 centimeter is 100. 100 centimeters is 1 meter. So now if we calculate, you can see the area in meter square has been found and centimeter square also has been found. Finally, to do the what if scenario, that what if the, I forget what is given here, how would the flow velocity change if the inlet temperature were 900 degrees Celsius? So we go back and say simply that, you know what, if the inlet temperature is 900, we just change this P1 to 900, this one to 900, given variable, we do a calculate to make sure T1 has been changed to 900. And now to update all the calculation, remember our current area is 236. If you do a super calculate, voila, you come back here and you pick up the answer. So because the temperature has been changed, that is affecting the specific volume at the inlet, which is affecting the density, and hence the area has been changed, has also changed responding to the changed condition.